Hello, my name is Victor Huilcapi. I'm a researcher at the Universidad Politécnica Salesiana of Ecuador. I'm going to expose my paper. The presentation is organized in 5 sections. In section 1, I will talk about the motivation of the research. In section 2, I will make a brief introduction on design based on multi-objective optimization. Later, in section 3, I will show the proposed methodological approach. In section 4, the proposed methodology will be applied to control a nonlinear multivariable system called boiler turbine unit. Finally, the conclusion will be shown. In the multivariable control, there are two main approaches. Each approach has advantage and disadvantage. These are centralized control and decentralized control. To establish loop pairings in multivariable systems, the interaction that occur between their inputs and outputs are generally measured. A seminal word to measure the interaction of the inputs and outputs of a multivariable system is called the relative gain array, and was proposed by Bristol. After Bristol's work, other methodologies were present to carry out decentralized control of multivariable systems. The traditional methodologies that exist for selecting loop pairings in multivariable systems, they can suggest different combinations of input-output pairings for the same multivariable system under the same operating conditions. They associate the selecting of loop pairings independently of the tuning of the control structure. To exemplify the above, a preliminary example will be analyzed below. A system with two inputs and two outputs is shown, where U1 and U2 represent the inputs and Y1 and Y2 represent the outputs. The process model is represented by G. The time delay are in seconds and the system gains are scalar. The RGA techniques suggest a diagonal control of the system. The DRGA technique suggests an off-diagonal control of the system. The divergence of results proposes the idea of analyzing the problem from another approach. The same controllers proposed in reference to are used. These are PI controllers for each control loop. In order to tune the controllers, an optimal tuning approach is proposed, minimizing a single objective. The quality of the control is evaluated using as performance indicator the integral of the square error value and the integral of the control action value. The table shows that the off-diagonal controller is better than the diagonal controller. Two questions are stated to discuss more details about the selection of control loops. The first question is, what would happen if PID controllers are used instead of PI controllers? The controllers shown are proposed to answer the question. The performance of each controller and tuning parameters are detailed in table shown. The table shown that the diagonal controller is now better than the off-diagonal controller. The second question is, what would happen if we choose a different indicator to measure the quality of control? To answer this question, the quality of control is evaluated using the following performance indicators. the integral of the absolute error value and the integral of the absolute value of the derivative control signal. The table shows that the diagonal PID controller is better than the off-diagonal PID controller. In accordance with these findings, the motivation emerged to propose a new methodological approach to select input-output pairings in multivariable systems with a multi-objective optimization approach. In a multi-objective optimization approach, it is possible to analyze the problem in a multidimensional space, where the designer's preference plays an important role in selecting optimal control loops. Now, I'm going to explain the introduction to multi-objective optimization. A multi-objective optimization design procedure consists of at least three stages. In stage 1, the multi-objective optimization problem is defined. In stage 2, the Pareto from is obtained using a multi-objective optimization algorithm. It is important to mention that the proposed methodology is independent of the optimization algorithm used. Stage 3 corresponds to decision making to analyze and visualize the solution of the Pareto fronts. The multidimensional fronts visualization tools called label diagram was used. More information about the tool is shown on the website. Now, I'm going to explain the methodological proposal. Consider a multivariable system with n inputs and n outputs as shown in figure. A control alternative for the multivariable system is proposed. This control alternative is known as a design concept and is defined by two aspects. First, a vector that contains all the controllers for the system, that is, the controllers for each output. Second, a selection array of control loops that connects the outputs of the controller with the input of the system. This array establishes the input-output pairings. Now, each controller is optimally tuned using a parameter vector that contains all the controller parameters and must have an associated loop pairing array. The optimization of the design objective sets the tuning of the controllers for a type of controller and a loop pairing array. The methodological proposal is shown on this slide. In Station A, the problem is defined. Multi-objective optimization is performed at Station B. Station C is the decision-making stage. If the performance of the system does not satisfy the designer, it is possible to return to Station A and start the process again. Now, I'm going to explain the application. The methodology is applied to control a nonlinear multivariable system called a boiler turbine unit, where S1, X2, and X3 are the system state variables, and denote X1 is the drum pressure, X2 is the electrical power output, and X3 is the fluid density. The inputs U1, U2, and U3 denote U1 is the valve position for fuel flow. U2 is the valve position for steam control, and U3 is the valve position for feedwater flows control. The outputs Y1, Y2, and Y3 denote Y1 is the boiler pressure, Y2 is the electrical power output. The output Y3 is the drum water level, The output Y3 depends of steam quality and the evaporation rate. This slide shows the main operating points of the system. Point 4 is the nominal operating point of the system. The methodology was applied when the system was at this operating point. Two design concepts are proposed with their controllers. Each controller has an associated parameter vector. In the multi-objective optimization process, 6 design objectives are minimized to evaluate the performance of each controller. After the optimization process, the following results were obtained. The figure shows that one design concept is better than the other. The table shows that the blue design concept is better in all design objectives than the brown concept. This slide shows the system outputs for two select controllers on the Pareto fronts of each design concept. It is possible to observe that the blue controller is better on all outputs than the brown controller. Finally, the conclusions. The applied methodology allows both the optimal selection of loop pairings and the optimal tuning of controllers. An interesting aspect is that the methodology was applied directly to the nonlinear system. That is, it is not necessary to linearize the systems. The proposed methodology has embedded the selection of input-output pairings and the optimal tuning of the controller in what is known as a design concept. One design concept was better than another in all design objectives in the analysis scenarios. The application examples show how the designer's preference as well as the optimal tuning of the controller have important roles in the selection of an optimal loop pairing. Thank you very much for your attention.